nuestro speaker, profesora Patricia Alonso Ruiz. Nos va a hablar sobre un tema relacionado con fractales, que en inglés sería hacia el problema isoperimétrico, cómo se puede medir el perímetro en fractales. Debo de mencionar que Alicia se graduó tuvo su doctorado en la Universidad de Siegen y actualmente ella trabaja como profesora asistente, no sé, dice realmente en inglés, Tenure Track Assistant Professor en la Universidad de Texas A&M. Y su investigación está relacionada con probabilidad, análisis y aspectos geométricos de procesos estocásticos en espacios de estructuras, en español serían rudas. Entonces deben ser manifolds, fractales. Y por ende, Patricia, bienvenida a nuestro coloquio de matemática y puedes iniciar cuando quieras.
Vale, muchas gracias. Bueno, muchísimas gracias por la invitación. Es una suerte que podamos hacerlo así, bueno, y esperemos que a lo mejor en un par de años lo podemos hacer de verdad, en persona. Solo deciros que les estaba comentando antes que voy a hacer la charla, la voy a dar en inglés porque mis matemáticas yo las he estudiado en inglés, entonces es lo que más rápido puedo hablar, pero que si tenéis preguntas o lo que sea, podéis preguntar en inglés, en español, podéis preguntar en francés a lo mejor, si puedo, os contesto también. ¿De acuerdo? Con lo cual con esto voy a change in English. And speak about what is the isoperimetric problem and how can we try to pose this problem in a space that is a fractal, because this is the type of things that I work with. And so the talk is going to be path along to get to the formulation of this problem, and in the way we are going to see what are the ingredients that we need for this. So we're going to look at things like what is Hausdorff measure, what is a fractal, and I will explain you at the very end some new ideas that we have developed, how to measure the perimeter of a set inside of a fractal. So let us start from the very beginning. So if you read the abstract, this was what I was talking about. So let us put ourselves in a sort of a real life problem. So we imagine this farmer, and he or she has a budget and can buy some amount of fence. Yes, so like some amount of fence. And if you really care for your animals, then you would like them to have as much space as possible so that they can play around, right? So the question that you ask yourself is, well, I have this much fence, now I want to build some sort of object and I would like to maximize the area enclosed by this. So this is sort of the question of our farmer. I have a fixed L, so this is L, the length of the fence, and I'm asking myself, well, what is the geometric object with this perimeter that has the largest possible area? Okay, that's the problem. So now we are going to try to formulate this in more mathematical terms. Okay, so first of all, we ask this ourselves in R2 in the plane. And so now what we are asking ourselves is, what is the subset of R2 with this perimeter L that has the largest possible area? So the answer to this has actually two parts in some sense. And the first part, this is step one, was given by Steiner in 1838. And what he discovered is that if we have this fixed length and we take any set that's sort of nice, we will talk about what nice is later, and has this perimeter L, then if we look at the area, this area is going to be at most L squared divided by 4 pi. Okay, so this is sort of an upper bound. And this inequality is what is known as an isoperimetric inequality. So perimetric inequality. And okay, maybe talking a little about language. Why is this called isoperimetric inequality? Well, of course, it is an inequality. This is why it is called an inequality. But then, why is it called isoperimetric? Well, this word comes from Greek. So if you have seen, so we have this iso and then the perimetric. So perimetric comes from perimeter, and iso means same. So we are looking at sets that have the same perimeter. And among all the sets that have the same perimeter, this inequality holds. Yeah? So it's a way to, so this actually this inequality has some story, language story in it. So this is the first step, yes. And the reason why this is the first step, because this is only giving us a bound. So it's saying at most it's going to be this number. Now there is a second step, and this was not very clear at the very beginning when Steiner was thinking about this. Was not yet clear whether there is at all a set that really maximizes this inequality. So whether there is a set for which the area really equals L squared divided by 4 pi. So this took a little to settle, but it did happen, no? So in 1879, Weierstrass figured that the area equals L squared divided by 4 pi when the set that we look at is a circle with a particular radius, namely this radius L divided by 2 pi. Yeah? And in fact, it's saying, if we look at it, it says if and only if. So this is the only set that satisfies the equality. Yeah? And just for like so that we make some small computations. So we are going to do some small computations during the talk today. So it's a small computation number one. Let us check that the area of a circle with this radius is actually that thing. So, okay, now let us go back in the, I don't know, our reminders from maybe high school. What is the area? The formula for the area of a circle of radius r. Someone know this or recalls this? I tend to speak to the public, even if it is online. Sorry. So does someone remember what is the formula for the area? You can also write it in the chat if you don't want to speak aloud. This is the area of a circle with radius r. Area equals
R cuadrado.
is what? R?
Pi R cuadrado.
Perfecto, pi r cuadrado. So now we substitute pi 2 pi square. And now magic, right? I mean, it's not magic, but this is the nice thing about it. So we have pi square, yeah, 2 squared 4, and then this one with this one. Ha! This is exactly the thing. So this is kind of nice, nice. Yeah. So there we go. And so now we know what if we go back to the pictures from the very beginning, this is what happens. So if I am a farmer, what I'm going to do is I'm going to draw a circle with that area, and my hens are going to be very happy about that. No. So this was sort of the beginning of the story, we looked at it in 2 dimensions. This is kind of nice to make pictures. Now, mathematicians like trying to, now we know this in 2 dimensions, what happened in higher dimensions. So let's have a look at what happens when we are in 3 dimensions. And we are going to see that even the language is going to be different. We need some more language. So, okay, let's have a look at, R3. So the question that we had before said, given a fixed length, okay, number L, which subset with perimeter L has the largest possible area. Now, if we are in R3, I'm going to try to draw something in R3. Let's see. So in R3, I need, like this type of thing. So in R3, we don't really talk about the perimeter of a set. What do we talk about? It's not rather the perimeter, but like, how do we call this? It's not the perimeter.
Surface.
Very good. It's the surface and the surface area in this case. Yeah. So it's the surface and the surface has an area. So instead of perimeter, we say, so we can fix the number. Now L is fixed still, but now it's not the perimeter, it's rather the surface area. And what do we say instead of area? Now it's not the area where we are looking at. We are wrapping something. And the inside now is not area, is
Volumen.
Volumen, exactly. So this is a volume. So we see that even the words are different. And the answer was given by, at least the one I know is by Schmidt in 1939. He did like what Steiner had done in general, and he said, well, if we want to solve this thing, the maximizer is going to be a ball, so a sphere. And this is more difficult for me to draw nicely, but like this one is going to be the right one. And I am not writing, so he gives the exact radius that we need. I'm not going to write it because things get a little more complicated the higher you go in each dimension. But this is the solution to the problem. Now, mathematicians now want more. You want more. You know how to do it in 2. You want to know. Now you want to do it in any dimension n. So how do we call things in n in general? So what happens with the surface area? What happens with the volume? What do we do? And for this, we have to thank Hausdorff, who in 1918 came up with this concept of the Hausdorff measure. And so let us have a look at how this definition works. Again, this is another 2-step thing. So we are considering any set, and I am drawing things in 2 dimensions because it's the place where I can draw better. So first thing is we are going to look at some delta, you see. So we're going to define the following thing. For some delta, which usually is small, we are looking at the smallest, the infimum quantity that we can write like this. So let us have a look at what is this. We are looking at what's called a delta covering of the set. And that means all these UIs are like small sets, and they are going to cover the space. And they don't have to be all like the same or anything, and they can overlap. Well, it should overlap, yeah. The only thing that we are asking is that the diameter of these sets cannot be larger than delta. Okay, so the largest one will have diameter delta. Could be something that's smaller, but yeah. So this is how that looks like. And now we are taking all the diameters of all these pieces that are covering the whole thing. We are raising this to this number D, no? Which can be anyone. And then we are adding everything up. And this thing can in principle be anything, could be 0, can be infinity, can be something finite. But we can always define it. And once we have this is now like we have some sort of approximation. And what we are doing in the second step is something that we usually do, which is letting delta, this sort of coarseness, shrink. And we are getting finer and finer and finer. And this number, this limit, is what is called the d-dimensional Hausdorff measure of E. Okay. So let us write this here, d-dimensional Hausdorff measure. So this concept turns out to be very useful because it can help us to define volume and surface area or perimeter with much more generality. So this is what happens in Rn. So we think again of our set E. Now it could be in Rn. I cannot draw it. I can only draw in R2. But and we say that it has a smooth boundary. So in the sense that, you know, I can sort of draw it without making many and the volume measure, so the volume of the set is going to be the n-dimensional Hausdorff measure of E. And for the perimeter, or say for the surface area, what we are going to do is we are going to look at the boundary of the set, and we are going to take the n-1 Hausdorff measure of it. So because what's happening here, if we see this thing in 2 dimensions, we have that E has some area, right? And now if we look at the boundary is kind of 1 dimension less because it is only a curve. So, right, so if I sort of disentangle it, it becomes a curve. So that means for us now, if we try to think of, so now we can talk about this measure in any dimension. And for those we can sort of draw, we have words, specific words. So when we are in dimension 1, as I was saying, so in dimension 1, we only have sort of lines, curves. The volume measure, how do we call the volume measure in the n dimension? Like if we take an interval, what is the one thing that we can?
Distancia.
La distancia. La
Longitud.
I want to call it the length. I don't know how you say the length. La longitud. La longitud. Yeah. So this is la longitud. So let's put this here, the length. And what about the perimeter measure? What is the perimeter of a line? What is the boundary? Boundary tells me when it stops, right? So what are the limits of this thing? So what are the limits? Beginning, end, 2 points. So what is the measure?
0.
So it's exactly. So it has volume measure 0. But if I really want to measure it, I have to go 1 dimension below, which is dimension 0. Dimension 0 is counting measure. Count. 1, 2, 3. This is counting. And this is why the perimeter is like, you know, counting. Just count. And when we are in 2 dimensions, we have seen this already. We said that the volume measure, what was the volume measure in 2 dimensions?
Area.
The area, perfect. And what was the perimeter?
Perimeter.
The perimeter is tautology. And in 3 dimensions, we say the volume measure is
Volumen.
volumen, so volume, and this we use the same. And for perimeter, we use
Área superficie.
area superficie. Let me
Surface
write
area.
surface area. And then for more dimensions, we don't have the words. I mean, we don't have any specific word. We just talk about volume measure, perimeter measure. See. Now we can write down the isoperimetric problem in N using this new language. Yeah. So fix L number. We want to find a set in N that has perimeter measure L and the largest possible volume measure. And there is this thing here is the formulation from Alexandrov in 58, which is just telling us this is the isoperimetric inequality in general. So you see here we have the n-dimensional Hausdorff measure of E is less or equal than some constant. It's going to depend on n. And then, yeah, so this thing here, if we look at this in n equals 2, what is this? Well, we said that the 2-dimensional Hausdorff measure is the area. So this was the area. Oops, area is less or equal than some constant. Okay, don't talk about a constant for now. And now here, this thing, this is just the length. Yeah, so this is giving me n minus 1, 2 minus 1 is 1. Yeah, so this is going to be, this thing here is the perimeter. And everything is raised to which power? Well, if I put n equals to 2, what I have here is 2 divided by 2 minus 1. 2. Yeah. And so here we are seeing again, remember before the perimeter was L, so the perimeter is L. So this is when we are getting the constant. So this is C2, the constant, and then L square. This is where we see the L square. Oh, we had this before. And okay, equality holds when we have a ball. And this is nice. Yes, now we can say something about what happens in a general n dimension. Now, I am personally more interested, interested in what happens when we are looking at objects that don't have an integer dimension. So something that would look like this. So now my farmer, let's think of the farmer wants to put a net or a filter, something that has a lot of tiny holes. And you ask yourself the same question. You have some finite, you don't know exactly what, but you would like to delimit an area, sort of. Now we need to think about, okay, what is the perimeter here? What is the volume measure here? And so this is what we are going to try to understand in the next slides. How do we go on searching this? So we are now on the quest of seeing what is the volume measure, what is the perimeter measure here. How do we define that? And we are going to start by the sort of a more straightforward in some sense one, which is we're going to look at the volume measure. Yeah. And we make the following observation. So remember that when we looked at the definition of the Hausdorff measure, it didn't matter what the D was. This D could be any number. Could be 1, 2, 3, but it could also be some fractional number. And this brings ourselves to the concept of dimension. And remember, we said that was the D-dimensional Hausdorff measure. So what does this dimension actually mean? Where does it come from? What is the right dimension of a set? And I have here these 2 pictures that I want you to I want to go over with you so that we see this concept of the dimension. So left-hand side, we have like my favorite R2 set. And what we are going to do is we are going to look at the value of the d-dimensional Hausdorff measure of this thing. And on this side, we are looking at different d's. So what is the value of the one-dimensional Hausdorff measure of this set? Does someone know? Like, so what is the length of this red piece? What is the length? Remember the dimension. What is the length of this? It's pretty long. We try to measure the length.
Infinite.
Is what? Infinito.
Infinite.
Yeah. So it is infinito. So it's just too long. It's too long. Infinito. So it will be kind of here. I'm putting the infinito here. And what happens with 3? Let's look at what happens when the dimension is 3. What is the volume? El volumen of this red region?
0.
0. No volume. So it's 0. Well, it turns out that if we continue doing this, this is going to happen all the way long. This will happen all the way long because 4 dimensions, it's nothing. But there's a sweet spot at number 2, where if we look at what is the Hausdorff measure of this is somewhere which is not 0, and it is not infinity. It's somewhere, drops. Well, the same thing happens with a fractal, like this is my favorite fractal for today, the Sierpinski gasket. We can do the same thing. We can start computing, and same thing is going to happen. It's going to be infinity, and then at some point it's going to drop, and it's going to become 0 forever. And the sweet spot turns out to be not in 1, not in 2, is somewhere between 1 and 2. Yeah. So the sweet spot is here. We are going to see exactly what the sweet spot is in a second. Yeah. And so this number, so this falling from infinity to 0, this falling is the spot that tells me this is the Hausdorff dimension, the correct Hausdorff dimension of the set that I am looking at. Yeah. So now you think before yourself, okay, cool, very nice. How do you go on computing this thing like in real? Are you really going to always look at when does it drop? And I'm going to tell you, well, there are some classes of sets, some classes of fractals where some mathematicians have done great work to make our lives easier. And for those, we can compute them in much easily. And those are the ones that I would like to show you here. Those are called self-similar sets. And self-similar set, again, this is one thing with the word tells you what's going on. Self-similar set means it's made out of copies of itself. So if we look at the Sierpinski gasket here, we see that there are 3 copies. Yeah. So one of the copies, what's happening is that I am squeezing the thing and moving it to the left, bottom left. So this is like a function. I can think of this as a function. Let me call it psi 1. Then I have the blue one. The blue one does the same thing. It's going to squeeze everything a little and then move it up to the top, second one. And then the third one, like let me put this one here. The third one is doing the same thing, bringing everything to squeeze, move right bottom. Now, if, okay, so now we have this, what are called similitudes. Those are these mappings, these functions that they are called similitudes because they bring a triangle into a triangle again. So nothing is really changing that much. And they have a ratio, and the ratio is by how much are we squeezing things. So what is the ratio of these mappings here for the Sierpinski gasket? Let us imagine that this, let us imagine for now that this, if I measure this is 1, how much is this? I tried my best to be precise, to be. So what do you think? It's like maybe
Un medio.
un medio, perfecto. I just divide by half. This is un medio. It's un medio for everybody. So all these L's here, all these L's, L1 equals L2 equals L3 is a half. And yes, we see here, this is what is happening, that if we look at this F, here's my fractal. The fractal is just V1, no? Union, the second, union, the third. Very nice. So now for this type of sets, Hutchinson in 81, so we are moving forward in time, he figured out that if you want to compute the house of dimension, the only thing you have to do is you have to solve this equation here. So you take all your all these contraction ratios, all these ratios, you raise them to the power d, you don't know the d, and now you solve for d. Yeah, so we're going to try to do this. First of all, let us try this with the interval, which is not a fractal, I mean, not a true fractal, but this is a similar set because we can understand the interval. I can just divide it into two pieces, squeeze, move to the left, squeeze, move to the right. Yeah, so we have two. And in this case, what are the ratios of this? So I can look at phi1, phi2. And what are the ratios?
1/2.
1/2, very good. So let us try the Hutchinson rule. Yeah, so Hutchinson rule is telling me, okay, you have 2, so let's do 1/2 to the power of d plus 1/2 to the power of d should be 1. So, okay, this is 2 times 1/2 to the power of d should be 1. So 1/2 to the d should be 1/2, so d equals 133. I was trying to say that thing. Yeah, so this is nice. This is just the dimension of a line is just 1. So let us do the same thing with the Sierpinski gasket. Just remember what I was said. What were the ratios? We said L1 equals L2 equals L3. This was also 1/2. But now we have 3, which means that instead of having 2 times 1/2, we have 3 times 1/2 to the d. This should equal 1. Huh. So now the thing is a little more interesting. And now what is d? Does someone know what is d?
Log
Log, yes.
1/3 divided by log 1/2. Yeah, half. Yeah.
Yes, so we can do, if I want to just to avoid the 1/3 and the like, I can do log of 3 and log 2. You agree with me?
Yeah.
Yes?
Yeah.
That this, we can do this as well, because it is like it's like 2 to the d equals 3 as well. Well, this is the Hausdorff dimension of the Sierpinski gasket. So this is the sweet spot where things change. Yeah. So this is the Hausdorff dimension, and this is going to be very important for us because now, okay, we can start at least saying the first part or the last part of the isoperimetric problem. When we talk about the volume measure now, what we are going to say is, oh, okay, well, so instead of volume, so for volume measure, what we are going to pick is the house of dimension at the correct, with the correct dimension. Yeah, so this is the volume measure is this. Yeah, so okay, so the house of dimension tells me what is the correct dimension to choose the volume measure here. And now still we have this issue with the perimeter. Well, I mean, it's not an issue. We need to see what's happening with the perimeter. So how do we find the perimeter? And for the perimeter, we're going to try to recall what happened in general so that we can try to see whether we can mimic this. Okay, so in the Euclidean case, we said that the volume measure was given by the n-dimensional house of measure of this. Yeah, and this one, this PA, this is what I want to call the perimeter. So what was the perimeter? Someone remember how we define the perimeter?
n-1 half dimension.
Mm-hmm. Yes.
Of
what?
Of the boundary.
Of the boundary. Perfect. This is what we did. So now we are going to try to do the same thing. And if we are in a fractal with dimension dh, we just said, we agreed that we were going to take the house of dimension at their correct dimension. Yeah, so the house of measure at this correct dimension of E. And now if I naively go and say, okay, so now I'm going to exactly do the same thing, and I'm going to take the perimeter to be the h minus 1 of the boundary. Well, if we do this, which is the first thing that you would try to, unfortunately, this doesn't work. Why does this doesn't work? Well, because first of all, if we look at the house of dimension, so depending on what the boundary of my set is, so if I'm looking at this set, the boundary is something like is everywhere here, somehow here. And what happens is that if we do this, we are subtracting too much. So doing the house of dimension minus 1, so subtracting a full dimension in some sense, full one dimension is too much. So we would end up having everybody has, anything you take has perimeter 0, anything. So this kind of doesn't work. So we need something else. And here is where I am going to tell you something that I have started working on. Well, I started working on a couple of years ago with a series of collaborators where we are using heat, so a diffusion process, proceso stocástico, heat, how heat diffuses. We are using this in order to measure the perimeter. And to tell you a little of the story, this is of course not our just coming from nowhere. We got this idea from a result du Tout-Ledoux, a French mathematician in '94, who looked at this problem, how you can define the perimeter of a set, but like in n, like in somewhere where you already know what it is. So we know already that this perimeter is the n-1 of the boundary. This is what we know, and this is fine. And what he figured is that you can actually write down that perimeter in this very strange way, which I'm going to explain you in a second, that has to do with several things here. So let's look at what are all these things. So in this right-hand side, the first thing here that we see is this xt. This xt, capital X, is denoting what's called Brownian motion. So Brownian motion is precisely, so okay, let me write this first here. Brownian motion on, well, wherever we are, yeah, Rn. So Brownian motion is the mathematical model for having a particle, so the movement of a particle. So let's imagine a particle in E and we hit it. So we put some heat on it and then the particle starts moving, yeah, starts doing some random movement, and this random movement is described or characterized by a Brownian motion, yeah. And so what this quantity here is doing, yeah, so you see here, this is x naught. This x naught is the beginning of the movement where the particle started. And all these things that I am, this quantity here is counting how often the particle is going in or out of the set. It's counting, this is what it's counting. So this is sort of times that, well, boundaries cross in some sense. Boundary crosses. Yeah. But this is random all, right? And so because all this is random, what I am doing is taking the average, the expectation. So the expected number of boundary crosses. Yeah? So this is expectation. And what else do we have here? Well, we have here this other piece, India, which tells us that what we are doing is we are looking at these boundary crosses at very small times. So we are looking what happens at a very short time. And we are rescaling everything with respect to the time. Yeah. So how many boundary crosses per amount of time? And the amount of time has this square root, which is very particular of the case of the Euclidean space. And so this is what Ledoux found out.
Sorry.
Yes.
I have a question. The expectation is with respect to the initial point, and that's why it's an n-dimensional measure, or?
Very good question. So I am taking the expectation with respect to the house of measure of the underlying space.
Okay, thank you.
Yes. This is, sorry, I forgot about that, because this is also going to change. We are going to see what happens now. So we try to do the same thing. This is a result that has been published this year. So this is like a very new in some sense. So we are doing exactly the same thing. And we are looking at what we call a PCF nested fractal. I'm going to show you a picture in a second, what this looks like. And so as you see, we are doing exactly the same thing. We are sort of copying what Ledoux did. Now looked at, and this is now perfect, this observation. Now what we are doing is taking this expectation with respect to the d-dimensional house of measure of the set. So no n, but the correct dimension. And what we also see is that here we don't have the square root, we have a different number, which we can sort of compute in terms of the house of dimension. This is here, and this another dimension is what's called the walk dimension, which is not very relevant at this moment for us. So it's just some number we can compute. Well, at this for particular sets we can exactly compute it, for those we can. And the nice thing is that with this construction that we are doing, if we look at the Euclidean case, everything works out nicely, and we end up having we have that this exponent really is 1/2. So 1/2 corresponds to the square root. And having this definition, which is sort of also like a theorem, because we need to understand what is the right exponent so that this limit gives you something that's not zero or not infinity, so something that's meaningful. With this, finally, we are able to do our isoperimetric problem. Before, let me tell you, this is the picture about what type of fractals we can work with. So they are called PCF, for post-critically finite, and they are, what this means basically is that if we look at, we can disentangle them by just choosing finitely many points. We can, yeah. So this again, like this, we can chop them into equal pieces like this. And so now we can, as I was saying, this is we made it to the end, right? So now we have this equality. This, so let us say what Alexandrov did long time ago. Said, look at the volume, then dimensional, the volume measure is less or equal to some constant times the perimeter measure. Well, we obtain the same result for us. Now, we see that these constants look a little complicated or a little different. Remember that okay, so the perimeter, we also call this thing the perimeter before, right? So it's the same perimeter measure, and the numbers are a little different, but the nice thing about them is that if we look at what happens in Rn, well, in Rn, what is the Hausdorff dimension? The Euclidean space. What is the Hausdorff dimension?
N.
N, yeah, this is why we say it is N. And well, there's alpha 1, I told you before, even though we haven't, this would be like another complete talk. Is this a half? We can compute this. And in the particular case of the Euclidean space, we also know that this walk dimension equals 2. So interestingly, if we look at what this number is, where this is n divided by n minus a half times 2. So we get n divided by n minus 1. And this made us very happy, because this means the theory actually really works. It coincides with what it should be in a particular, in Euclidean case. And this is so far what we have. Next questions that are there is, well, can you compute this perimeter? And this is part of current work, so it's still a work in progress with Fabrice Baudouin from the University of Connecticut. And then we are trying to see what is exactly the perimeter. And at least we can prove that this perimeter really coincides if we are taking the union of different cells. In that case, it's just the number of points as we would sort of expect, but it really does equal plus some constant. This is how it looks like. And so this is what's currently happening. What I would like to do in the future is solve the isoperimetric problem, right? So can you find a set that maximizes the volume when I give you the perimeter? And this is very, very, very much open. And with this very, very much open question, which I hope that maybe sparks you or makes you excited about this, all this story, I would say thank you. Muchas gracias. Y eso es todo.
Ok, gracias, Patricia. Démosle un aplauso a Patricia por la presentación. Y si tienen algunas preguntas, procedemos a